So we're Team 83 from Sandy Preparatory School. I'm Alessandra Anderson.
And I'm Kaitlyn Hughes. And our project is called Subatomic. So our project was to create a visual model of a hydrogen atom using both the Bohr's planetary model as well as the quantum model. We got inspiration for this project. My dad is a school teacher, and he said that he was having problems trying to explain atoms to his children. So we got the idea to create an accurate yet simplistic model of an atom that could be used as a teaching aid.
Okay. And we decided to go with hydrogen because, in fact, this is the only atom that works with the Bohr model, just to do with the electrons. And since we wanted to do both, this seemed like the obvious choice. And there are just some basic facts. So it has one proton, or for the atomic number, which also means one electron. So that's what we were dealing with, and just some other information about that.
So we started out with Bohr's atomic model, since it is more simple than the quantum model. It's also known as the planetary model. And if you imagine the solar system, the proton, or the center of the nucleus, would be the sun, and the electron would be a planet orbiting around it. And as you move up in protons, as well as electrons, the energy levels gain. However, this doesn't really work with the atomic theory. As you can see, the nucleus would be the proton. And since we're modeling hydrogen, there would only be one electron orbiting instead of the several that are on that picture.
Okay, and also an electron in hydrogen orbits at 0.0593 nanometers at constant rate, like at the center, unless it jumps levels and gives off energy, but it's not really important. Okay, and then the quantum model, this is a theory in physics that states that the electron has both properties of waves and particles. And so basically it says we cannot judge where the electron is at any given point in time. Because of this, instead of actually being able to model like the planetary model, it creates an electron probability cloud. And I'll go to the next slide here. And that's what's modeled right here. And if you see with hydrogen, which is the 1s orbital here, where it's dark is where it is most likely to be, and where it's lighter, it is less dense there, less likely to be there. It can go beyond this cloud, but 90% of the time it will be in this cloud. And also, cool, going back to the Bohr's model, it's mainly at the same length the Bohr predicted. And the other two models are just if you go up in higher energy levels, the probabilities for those.
We had to use a probability curve when creating our model because, as Alessandra stated, an electron travels in a random area around the center of the atom. However, it still tends to follow general laws. We found this probability curve, and that is the equation for the curve. And as you can see, the highest point, or it is most likely to be, is right at 0.0593 nanometers.
Okay, and actually, in order to implement this into code, we had to integrate a previous equation, which comes out to be that right there. And this is a very small graph of what that actually looks like. It's very simplistic. I can actually include the numbers there. I forgot the program for that, my fault. But basically what this shows is that in the area below the curve, it's going to be most likely in this area, and the white area is not going to be, but every now and then it will stretch out that far.
We also used a random number generator to determine the angle that the electron would be traveling at, as well as its position and its distance. We factored the probability curve into the random number generator because even though the number is random, it still follows a certain path.
Okay, and since our model is a three-dimensional model, we had to deal a lot with the matrix to get the rotation matrix, basically, because we're dealing with three different axes, x, y, and z in our model. And in order to get the electron to rotate around completely, we had to actually keep it on one plane and rotate the entire plane around. And so that's what's happening here with the bottom is actually part of our code We had to actually write out the matrices and what they would equal there. So it's that.
The law of conservation of angular momentum also helped increase the accuracy of our model. It states that as an electron will gain momentum as it moves closer to the center of the nucleus, and it will lose momentum as it moves farther out. So basically, when you're looking at the model, it appears that the electron is moving faster when it's towards closer to the center of the model, and moving much slower as it, moves out.
And it's because velocity is inverse to the distance. And so if the distance is further away, it has to have a slower velocity, where if the distance is smaller, the velocity has to be greater.
We implemented several keys so that you can play with our program when you're, looking at it. You can zoom in and out so you can get closer to the proton or further away, pressing X or Z. You can also change the path of the electron to make it to more of a Bohr model or a quantum model. You press D to randomize the path of the electron, moving it towards a quantum model. Or you can press the left shift D key to force the electron to move on one plane, making it the Bohr's model. You can also change the velocity of the electron, pressing F to make it go fast or S to make it move slower. And in order for us to get all of these pictures, we had to cancel the graphic update. So we programmed in the letter N. And it allows you to see the path. And this is also helpful in seeing the electron cloud of the quantum model.
And like how these work, the zoom in and zoom out, since we aren't a 3D graphics plane, there are two different planes. There's a back plane and a front plane. If we cross either ones, we lose the model because it just gets out of our camera vision, what we're looking at. The way that we can randomize this number, since we have a random number generator determining the angle which is going to rotate, so we can go at any angle and change, we had to smooth out the curves because originally it was jumping from like this place going over to the next place, and that didn't look so good. So with D, we can make it will smooth out the curve, but we get some, if you look at the picture over there, it smooths it out, but it's a little bit more extraneous, where if you look at the one below, it's on one plane. And so by making D really small, we force it, the angle can only change by like 0.5, whereas if it's D, it can change to anything. And so that pretty much puts a limit on the random number generator there. The velocity is going to just speed up the game time, or the time in our code, so it will not affect our angular momentum. I'm sure I explained the electron path. So in order to code this, we use XNA and C#. XNA is kind of like, I guess, a subprogram of C#. It is most famous because it's used to program Xboxes nowadays. And it's basically a graphics engine that C# came up with. And we just got online like a student version of it, and so we're working with that.